It was on before.
Yeah.
Ah.
Sorry.
Oh, okay. No, it wasn't on. There we go. All right. Thanks. So we talked about these spatially extended wave functions that were characterized by a quasi-momentum Q. But now I want to ask a different kind of question. Let's say I have an optical lattice, and I'd like to put an atom at just one site. And the reason that's interesting is because when we want to know the motion of atoms in optical lattices, then you'll want to start them in one place and let them go to another place. And so that kind of question about dynamics, spatial dynamics in a lattice, can't be answered unless we have some kind of reasonable wave function which puts an atom on an individual lattice site. So today what we'll do is we'll talk about that. We'll discuss something called Wannier functions, which localize the atom at a particular lattice site. How many of you, by the way, know what a Wannier function is already? So. Okay, great. I won't assume you've seen them before. So we'll talk about that localized wave function, and then we'll rewrite our original Hamiltonian in terms of localized wave functions, and we'll discover that hopping, tunneling between sites, is already contained in the original problem we solved. We just didn't use that language. So a lot of times in physics, it makes sense to look at problems from the momentum basis or the position basis, and that's just the kind of exercise we're going to start with today. We're going to go from the previous momentum eigenstates, quasi-momentum eigenstates, to a new kind of basis, which is spatially localized wave functions in position. Okay, so that'll be part one. Probably take about half the time. And then in part two of today's lecture, I'm going to talk about currents. So once we can discuss the position of an individual atom in a meaningful way, then I'm going to ask what happens if you have motion, which we'll define as a current. And a current is, of course, the kind of observable that is made in solid-state experiments all the time. What do you do if you want to measure the conductivity of something? You put a multimeter across it, you apply a voltage, which is a force to the electrons, and then you measure the velocity in terms of the current. Okay, so we're going to define that kind of observable based on Wannier functions and block functions. And then we'll get to the very end of the lecture to see what kind of current you get when you apply a force. Okay, so as before, I'm going to sit and write on my tablet mostly. And I did post some updated notes in the same link that I mailed you all last week. And I'll update those again for tomorrow as well. So to start with, let's talk about how we would solve the idea of localization without the lattice. So if we want to localize something in free space, well, I want to write some kind of wave function as a function of position, which is a delta function. You know, this is just saying that as a function of x, all of my density distribution is sitting at some location. If I call that xc, let's say. So I'm going to call this psi of xc. And that's just what you would get if you, expressed in the position basis a wave function which is at xc. And so this is an eigenstate of the position operator. So localizing things in free space doesn't sound so bad, but now what does that look like in momentum space? If I want to write that same wave function in momentum space, then I will take the k projection of this xc state. And for that, you might know, this is already e to the minus I k x c. So this is something that's very delocalized in momentum space, right? So as a function of k, if I wanted to write this function now kxc and ask what the probability amplitude is, it's just a constant across all k. So something that's perfectly localized in space is perfectly delocalized in momentum, which you all know from the Heisenberg uncertainty principle. In a lattice, we've talked already about how every band doesn't actually have a full range of momenta available to it. So let's try to localize as best we can with just one band of K space. So let's do this again now, except for a single band of momenta, then instead of writing out this kind of delocalized thing, I'm going to try a wave function localized at xc, which is now an integral from minus pi over the lattice to plus pi over the lattice wavelength dk times k states, okay? And maybe I'm going to choose some kind of phase to weight these k states at. Okay, so what I've done then is instead of using all of k space, I'm now only going to use just one part of it that goes from minus to plus the range of one Brillouin zone. Okay, so we call this a Brillouin zone. This is the lowest Brillouin zone. Maybe you call it BZ0, something like that. And so that's the limits of these integrals. By the way, KL is just pi over AL, and AL is the lattice constant. Okay, so if I want to find what this wave function is, what kind of weighting should I give each k? Let's just try the dumbest thing we can think of, which is let's not put any phase in front of these k vectors, and then we can do this integral. This is now just an integral of let's now ask what this is in position space. So if I want to write out this new wave function is a function of x, now I have this integral dk. I'm setting this phase equal to 0, and now I have the same plane waves I used to have. I'm sorry, the same plane waves and momentum I used to have. This is just e to the ikx, right? Yeah. And I'm going to integrate this from minus KL to KL. What is that? Do you know what that integral is? It's integrated in exponential. It's almost a cosine, except I need to, since I'm integrating over k, I have to take a 1 over x out in front. Okay, so this looks like, in fact, it looks like a sine of kx over x, and that's a sinc function. Okay, times some kind of normalization coefficient, which I'm ignoring. So this is sinc of x, and what does that look like? It looks like this. Okay, so if I started out with a delta function in momentum space and in position space, I told you that requires all of k space. But now if instead I restrict myself to one Brillouin zone, then I get this kind of sinc function here, which is an oscillatory thing. It's peaked at 0. And so I found a localized kind of function, but so far what I've told you about is a localization in the math I've done at x equals 0, because I had a sinc kx. But I really want to localize this at some arbitrary place, so I can put my atoms at any place in the lattice. And I do that with a translation operator. So what I can then do is say, I previously had this wave function, which I'm now going to call psi naught, which is this integral dk over all the k states. And that gave me this sinc localized at x equals 0. So some kind of oscillatory wave function. So if I want to instead have this thing displaced by one lattice site, let's say, then I want to apply a translation operator, moving things around by AL. And the translation operator is e to the minus p hat x for the translation, but I'm going to translate by AL over h bar, right? This is the generator of translations, and we talked about that last lecture. So this shifts something by AL. And so if I now apply that to this wave function, so I want to translate over something here, then I know what this is going to do is it's going to give me a wave function which is instead peaked one site over at AL. Okay. And what is that wave function if I write it out? Well, this operator applied here is just going to take the eigenvalue. This is a momentum eigenstate, so then I'm going to have p hat over h bar is going to be k. And that means that my new wave function localized at xc must be now the sum e to the minus I k xc times these k states. Okay, so now xc can be any lattice location, for instance, or any location. Anyway, I haven't really done this with a lattice yet. I'm just talking about plane wave states so far, but I'm anticipating that there's going to be certain positions I really care about. Okay, so that gives me, in the end, what I'm showing you here now, that if I apply this phase gradient with a slope given by the position I want the wave function to be at in position space, then I can localize it at xc here. And yeah, so, okay, so that's how you make a localized wave function at any position. So what we want to do now is take this free space discussion and apply it to the block states. So far, I've just applied it to the plane wave states. And so instead of having k here, which were plane waves, I want to replace these with the q eigenstates, which were the block states. And to remind you, they had the special property that if I take the translation operator times a lattice site displacement times any number of lattice sites, then if I apply that to the q state, I got, just like it would be for free space, e to the minus iq now, and then the displacement, a lattice times j times the original q state. Okay, so, oh, that's still big, okay. So this all is going to carry forward mostly if I consider placing these wave functions at integer multiples of lattice sites, then all the math kind of works quite similarly. And so inspired by that, we're going to now call this kind of construction a Wannier state. And we're now going to write it as W, J, okay? And what I mean by J is that this is something that's centered at the jth lattice site. So xj is at the jth lattice site. Okay, and so that's going to be the definition we're going to work with now. We have, I'm just going to write that out again. So we have some Wannier state, J, and we're going to try defining this as, for the first band, integrating over all quasi-momenta, e to the minus iq xj times the block function, okay? So this is the definition we're going to work with. And just like before, the translation operator works. So I could write this omega j, sorry, wj. It's not omega. There's a w. For any j. But they're all the same. Because if I push it over by one lattice site, because of the translational invariance of the Q states, it's all going to work out. So let me show you what I mean by that. If I apply the translation operator, I move by just one lattice site, the wj state. Let's carry that through. Now I have the translation operator applied to this inside the integral. Okay, but hey, this thing commutes, so I can commute this thing over to here, right? And so now, what is this? This is just equal to e to the minus IQAL times the original Q state. And that's the essential discrete translational symmetry of these states. And now if I stitch all this together again, this is e to the minus IQ, and now xj just has one lattice site added to it. And that's, of course, what I would have meant by the w state at j plus 1. Okay. So because of this, all Wannier states look the same in a given band. And by the way, what do I mean by in a given band? I could have been writing all of this stuff out as for an arbitrary band, and then I'd have to add a band index Q in, and I talked about how to do that last time. For a lot of the discussion today, I'm going to drop the band index, because if I work in a particular band, it's a closed Hamiltonian, and we're not going to think about band transitions today. But so each band has its own Wannier function. And so for the nth band, you can sometimes just drop this index and write the Wannier function for the nth band, because it's the same at every index. Okay. All right, so what do those things look like? I'll show you some pictures of those. We can figure out what they are spatially because we know how to write out the block function spatially. That was just the eigenstates that we solved for last time with this cosine Hamiltonian. Okay. So here are some examples. If I had a zero band depth that's zero recoil deep, then I get the same sinc function that we just derived for plane waves. But now as I crank up the lattice, you can see for a deeper lattice, then you can see the width of this is smaller than the width of this. Here, this, for zero lattice depth, we weren't really even contained on a single lattice site. You didn't get to this node here until the next site over. Whereas here, although the node is roughly in the same place, the width of this function is getting quite small. And that keeps going if I make an even deeper lattice, which is now 20 recoil deep here. You can see that these start to look quite like harmonic oscillator ground states. And I'll tell you tomorrow that there is an actual limit in which those ground states look correct. But there's something really special about the Wannier state, which is not shared by the harmonic oscillator state you might look, the Gaussian you might write here, which is that the overlap between these two wave functions is exactly 0. Even the wave function overlap between these two is 0. Because although they have amplitude at the same place, if I displace them and integrate, you can show that you get 0. You can kind of see that how this goes down here and provides something negative when this is positive, and this goes negative when this is positive, et cetera. And certainly you can do the math to show that if I take two sinc functions and I displace them by just exactly this amount, I integrate the product of these two things, I also get 0. So von localized states, they are orthogonal states. And I've created a basis which is now, just like block states, a nice orthonormal basis. Okay. So what else do I want to tell you about these? Yeah, question.
So in other words, when you increase the lattice depth, and so why this shape of this one-year function is getting affected? I mean, the optical potential and the shape, are they not independent? I mean, you are increasing the lattice depth,
Yeah.
but the leaking probability is decreasing.
Yes.
So why is that?
I will talk about that a little bit more, but why? Oh, well, so what I'm not showing here is an optical lattice to scale. So this is just normalized to having an amplitude of 1. In fact, you can think of this optical lattice as deeper, than, there's my drawing ability, but yeah. Okay, so you can see that this lattice depth goes up, and then the reason the wave function is more confined is just because the potential is becoming more and more strongly confining. And so the higher the lattice depth, the more this function becomes constrained.
So the same function contains some contribution from the lattice potential also.
No, actually, this is the 0 case. I shouldn't be drawing a lattice here, but it's just for reference because the spatial period of the lattice is important to the problem. I mean, these two sinc functions are only orthogonal if you displace them by one lattice site, and the reason they know anything about that spacing is because we chose one Brillouin zone of momentum. But it doesn't make sense, this isn't really a valid Wannier function for various reasons. You have to have at least a little bit of lattice, and so, yeah. I feel like I haven't answered your question. But. Okay, I will talk about tunneling probability in a moment, if that'll help. All right. So, yeah, why don't we do that now? So what we have so far is a nice orthonormal basis of Wannier states, and this has a kind of conjugate relationship to the block states. So I can write out a block state in terms of a sum over all the Wannier states, or I can write a Wannier state as an integral over, one of these things has to have a minus sign. It's this one, yeah. IQ xj times the q states. And so you can see that these are, nice Fourier transform pairs. Another way of writing that down, which is really useful, is to remember that the QWJ projection is e to the minus I QXJ and its complex conjugates. It reminds you a lot of how, Kx in free space was e to the minus I Kx. And in the same way, x and p are conjugate, just like the Wannier and block bases are Fourier transform pairs of each other. Okay, so anything I can do in one space, I can do in another space, and you'll see that's like the one-trick pony for the rest of this lecture. We're going to ask a question, we'll write it in a new basis, and then the answer comes out, okay? So. All right, let's do that, and we're going to start with writing out our Hamiltonian from last time, which was a first quantized Hamiltonian. We're now going to write it out in second quantized form. The problem is going to break down into various bands. So this is a single band Hamiltonian. And for that one band, then what we want to do is integrate over all q states the eigenstate we already found for the nth band, And then we want to ask how many particles have exactly this quasi-momentum. And so we'll count the number of particles that have that. And we'll do that with this operator here, which is, you can also write the number of particles at Q. This is a number operator. And this is an annihilation operator. And this is creation. If I'm being careful here, I should also write out a band index for all of these things. And what I'm saying is that if, for instance, I start with a vacuum and I create a particle at Q, then I've got one particle with that particular Q, okay? And if I were doing this carefully, I would also add the band index to all of these things. But that gets a little tedious as we write in everywhere. So I'm going to drop the band index and talk about single bands. But otherwise, remember they're there. Okay, so we'll drop this for convenience. By the way, notice the perspective changes when I go from that Hamiltonian I used to talk about, which just had p squared over 2m plus a cosine. That's a single particle Hamiltonian. Now, this new Hamiltonian, I'm going to sum over the number of particles at each Q state. And so this is now not the Hamiltonian of a single particle, but the Hamiltonian of a many-body problem. Okay, that's going to be a convenient notation for today, but it'll be an essential notation when we talk about interactions tomorrow. It's also convenient to talk about second quantization here, because what I'm going to do at some point is put a particle at a single Wannier state, at a single lattice site, and then ask, where does it go? So if I'm talking about single particles, it's also nice to have second quantized notation. How many of you are comfortable with creation and annihilation operators and second quantized math? Awesome. I'm at the ICTP. This is great. Okay. So, what we're going to do with this now is we're going to rewrite this in the Wannier basis. So what is the relation to the other kind of thing I might have, where if I want to create a localized particle from the vacuum at a particle at Wj, well, these two operators have a conjugate form. So as I said before, you can write out a creation operator for one of these in terms of a phase sum of the others. And I can go the other way. I want to integrate over all the q's and have a minus iq xj a q. Okay, so now this here are for Wannier states localized in space, whereas this and this are for the block states. By the way, if I cared about normalization and units and all these things, I'm an experimentalist, so I try to get the units right, but I'm not responsible for negative signs or factors of pi. But anyway, if you wanted to keep track of those kind of things and it's bugging you, then you can take all these dq's and make them dq al over 2 pi. And if it's also bugging you that one of these things doesn't seem normalized, well, you didn't protest when I wrote out a plane wave a moment ago. You can't normalize that either. So, in principle, what we need to do is think about a quantized volume with a box. And in my notes, you'll see that I put those two on equal footing. If you discretize the problem, so consider im lattice sites, then you can write the conjugate relations between Wannier and block functions that look exactly symmetric except for a minus sign. Okay, so I'm going to stick now to integrals over quasi-momentum and sums over positions, but you can show those two spaces have the same volume. So when we do that, what we want to do next to find out how Wannier states behave is we're going to take this expression here, and we're going to substitute it into here, and then we're going to take its complex conjugate and put it there. And so what are we going to have? We're going to have two sums over sites and one integral over Q, and we'll have another form for the Hamiltonian. So let me just write that out for you. What you get is, let's see, I'll make a little space here. You get a Hamiltonian now for a single band, which is the sum across J and J prime of a thing, which looks like this, integral dq. Now I'm going to integrate the energy, and I have these phase factors that come in. And then like that. Okay. All right, and you see what I've done. I've done the substitution, and we have a Hamiltonian. And it has a constant here, which has no operators in it. There's a number. And that number is multiplied by two operators that do something. They annihilate a particle at J prime, and then they create a particle at J. So in a lattice, what does that mean? It means that particles teleport. So let's say I start here, and then a little later, I'm here. Okay, so this would be, for instance, annihilating at J prime, and this would be creating something at site J. So what is that? Yeah, this is tunneling. So this is the phenomenon of a particle hopping from one of these sites to another. And the strength of that tunneling is just given by this integral here. So this we're going to define as, with a minus sign, which I'll explain in a moment, the tunneling coefficient. I'm going to call this T. There's a big battle that's ongoing, T versus J. So all condensed matter people write T. They use J to mean superexchange. And then all cold atoms people write capital J, and they, by superexchange, write JX. Why might a cold atoms person not want to use T? Because most problems are time dependent, and T is a good variable for time too. But that's not what I mean here. I'm going to use the condensed matter notation, and I'm going to say lowercase t is the tunneling energy, and it's a function of how far I tunnel. Okay, so it's a function of delta J, and what I mean by delta J is that's the distance from here to here. Okay, it's J minus J prime, or J prime minus J. Okay, so we have this nice integral, and we can now calculate tunneling from band structure. So if you remember last time, I was showing you all these curves that you get from diagonalizing the single particle eigenfunction. Now, if I take that dispersion relation of a single band, I can just take whatever its shape is, multiply it by the right factors of e to the IQAL, and integrate that out, and I get a tunneling coefficient. So what does that give you? Let's see. That's not what I want to show you. I want to show you this. Okay. So if I take the lowest band and I integrate it out by e to the I something, and I just want to hop by one site, I can calculate the tunneling energy. That's here. And that gives me this blue curve. Okay. And then if I want to tunnel further, I want to hop two sites instead of one site, do the same thing. I integrate my band by e to the 2I QAL, then I get this yellow curve, etc. Is that the further I want to go, the weaker the tunneling is. And also the ratio between hopping one site versus two sites gets bigger and bigger as I go to deeper and deeper lattices. So for really shallow lattices, it's maybe not so extraordinary to hop two sites, but for deep lattices, and here I go up to about 30 recoil in lattice depth, then hopping further away is less and less probable. So there's a very nice approximation I can make, which is to ignore everything but the nearest site hopping. And that's what's meant by tight binding. Tight binding meaning, well, the electron, when it tunnels, is kind of tight, doesn't go so far from home. It just goes to one site over. So if I ignore all tunneling coefficients except for the first one, I have a really nice, simple form of a lot of expressions, and we'll use that. Okay. Questions about this? Yeah? The dotted line is an approximate form. I wrote it down in the notes. I can write it here as well. It's an approximate form which comes from the property of these Wannier functions for deep lattices. An interesting thing about it is that you can't just use two Gaussian approximated on-site functions and ask for their overlap. As I mentioned, the tails are important. So it's a nice approximation. I'll include a reference in the notes. And you can see that formula fits pretty well. One thing about it is it has an exponential decay in the lattice depth. And so this thing falls off after you go a little ways, exponentially in the depth. And an exponential suppression is what you'd expect for a quantum tunneling through a barrier. So if a barrier height goes up, then the chance that you tunnel through it goes like e to the minus barrier height. Right? Okay. So let's write that out. This is something called tight binding. And in that case, you can show the dispersion relation. Well, first of all, the Hamiltonian in this tight binding limit is really nice and easy. It's annihilate a particle at some position and move one band over, okay, or do the opposite. Okay, so I'm summing over all sites. Maybe a way to write this to start out with is that integral I just showed you on the previous page sums over all j's and all j primes, including the reverse order. So I can go from j to j prime, or if those are some sites, I could go j prime j, or I could go j prime. Okay, and you see how those are just complex conjugates of each other, and so it's sometimes nice to just write it out in one index. So you could say, let's now just say we're going to sum over j and go to j plus 1. And then we could also do the reverse, and I'll write Hermitian conjugate. Okay. So this is the tight binding form. Another thing you might notice about this Hamiltonian is that if I'm just going to move over by one site, and I'm going to do that in every site of the lattice, this is like a shift operator. Everyone move to the left, or everyone move to the right, okay? And so instead of summing over all sites, you could just say this is minus t times a shift operator by one lattice site plus its Hermitian conjugate, which is a really simple Hamiltonian. When looking at this formula here, every time I'm thinking about a delta J, I have a delta J up here, but the eigenstates for plus Q and minus Q are the same. And so because of that, I can replace this whole thing here with a cosine of QAL times delta J. And if delta J is just 1, this is just cosine QAL. And so the tight binding approximation says that that's the only thing left. It's the only Fourier component I'm going to leave in the dispersion relation. If I left other Fourier components in the dispersion relation, then I'd get a non-zero answer for delta J equals 2, let's say. So the dispersion relation, the energy of the band, is something quite simple then. It's minus 2t times cosine of ALQ. So this kind of band is something you often see. What does it look like? If I want to plot the energy of the band versus quasi-momentum, I'm going to go from, again, minus KL to KL, and KL is just pi over AL. And there's a minus sign out front, so this is an inverted cosine. It looks like this, and the first band ends there. So I'm shifting energy 0 there, and this goes up to 2t at the edge, and it goes to minus 2t at the middle, which is q equals 0. And so the full band width here is what we call W, and that's 4 times T. So the bandwidth of the lowest band of the tight binding approximation is 4 times the tunneling coefficient. Let's see, anything else I want to say about this? I think that's it. Okay, so let me show you now what happens if we put a single particle into an optical lattice and start to iterate time by applying this Hamiltonian. And for instance, what if I start out with some initial state where I have no atom at any site except for a central site? Okay. So let's put atoms at only the middle site, and then I apply a Hamiltonian to do some kind of time evolution. What happens is that this atom can hop to its neighbors. So there's an energy T for us to have that one atom appear on the left. And there's also another possibility that I go to the right. Okay, and so either I go to the -1 state or I go to the +1 state when I started out in the 0 state. It's kind of like a random walk. I roll the dice, and every time I go left or I go right, except this is quantum mechanics, so it's not that I go left or right, I go left and right. Okay? And what happens if I do it again? Okay, let's take another time step forward. So now I have h squared times our initial one. And so there's two possibilities. Either this can move further or it can go back. And this one can go back or it can go further. And so so you see what we have. We have minus, oh, now I guess it's plus t squared. And so we have 1, 0, 0, 0, 0. We have two ways to get to the middle. And then we have one way of getting out to the other edge. So we could keep doing this. And remarkably, someone has. So here is some data from Marcus Greiner's group, where they initialize a line of atoms at the central site, and then they allow the Hamiltonian to proceed. They measure the probability to be in each of these sites. And you can see what we wrote down is just the very beginning here, that there's a probability to go out to the edge, and then there's a little more probability to come in. And that middle population, for instance, has some kind of oscillation as there's a odd-even alternation by applying the hopping operators over and over again. So after a certain amount of time, then this image is taken here, and you can see that particles which started here are mostly at the edges, following the kind of ballistic trajectory, moving at one lattice site per t, but there's also a probability still that you come back to the middle, and this is a histogram from experimental data over many different runs, okay? Okay. So when thinking about this kind of experiment, all we have to measure is position. We have to measure, yeah. Oh, yeah, right.
Why here we don't have that? I mean, why we don't?
Because there's interference. So the classical random walk cannot interfere with itself. So what we're seeing here is, so the question was, why don't we have a probability distribution in this case? It looks like the classical random walk, and the classical random walk is a Wiener function, I guess? Wiener function? Yeah. Right. So I think it's different because you get interference terms, basically. Classical particles don't interfere with themselves, so it's a different problem. Okay.
This experiment has a letter size of, I think, 22, if I count correctly.
Okay.
And it kind of like has a bias to like a certain way away from the edges. Does this change with larger letter sizes, smaller letter sizes?
You mean when you get to the edges, or?
Yeah, where it's localized, where if you look at the top, there's a bias for like 4 letter sizes. Yeah.
I don't understand. Of an edge here, or some kind of.
Not an edge.
No.
Maybe I don't understand the experiment. They have the letters, right?
Yeah.
Of a finite number of sizes.
Yes, but beyond what we're looking at here.
Oh, so it's just, it doesn't get further because they didn't devote time.
That's right, that's right. It didn't get further just because they didn't run time further. Now, eventually, they do run out of sites that are nicely equilibrated from each other. And the next part of the figure in this paper, when you look at it, is they apply a tilt to everything, and they show that atoms don't keep going, they come back, okay? Yeah, so there's some kind of response to forces that can localize you. But in this first experiment, everything is flat, and if they didn't run out of space, the particles would just keep diffusing.
Okay, so they were also really far from the edges.
Yes, that's right. That's right. Great. Okay. So we see here that atoms are moving. There's mass which is being distributed, and that's a current. And so I want to talk now for the rest of the lecture about how you think about currents in an optical lattice. So what I'm going to talk about is how a center of mass might move around. So first of all, let's define what we mean by average location, the position of a center of mass. I basically want to ask at every site xj, how many particles are there, and to count, I just have a number operator. And because I want the center of mass, not something extensive, I'm going to divide by the total number of particles to get the center of mass. So if I have a current across a net current in that cloud, the center of mass is going to move. It's going to be transported by the total current. And so it makes sense to write out something which is a current operator. And we'll show that if I use an operator of the form, which is the commutator of the Hamiltonian and x center of mass, then I get what I expect. So for instance, let's figure out why that might be. There's something called the Ehrenfest theorem, which says that the time dependence of the expectation value of an operator is I over h bar times the expectation value of the Hamiltonian commuted with that operator plus any kind of explicit time dependence of the operator. So let's apply this now to the center of mass position. If this is xcm and this is xcm, then you see that this whole thing here is then the expectation value of the current operator, as I've defined it, modulo factors of n, which we'll deal with in a moment. So as defined like this, the current operator is the thing which pushes around the position, in the average position of particles in the lattice. You can show that this has a nice form, and I give some details of this in the notes. You can show that this has the form sum over all pairs of lattice sites j and k times the tunneling between j and k and then the distance between them. So in the tight binding limit, we can simplify this further, and it looks like minus I TAL over h bar, sum over all lattice sites, and minus something like this. All right, notice this looks a lot like the tight binding Hamiltonian itself, except there's a few different things. First of all, what is the units? The units here are TAL over h bar, and so you can think of T over h bar as the tunneling rate, which is an inverse time, and this is a distance. So the current has a unit of velocity. The other thing you see is that it's imaginary, and I don't have a a plus between these two. I have a minus between the hopping here. So if I have kind of equilibrium distribution where I'm just as likely to hop this way as this way, for instance, I have two particles in neighboring sites, then the net current between them must be 0. When I get a non-equilibrium current is when I have a site with an empty neighbor. And then I can go one direction or I can go the other direction and I don't get 0. So currents average out to 0 when I have neighboring sites with either 0 or 1 occupation. Okay, so let's put this on hold for a moment and talk about something that seems unrelated at first, which is called group velocity, and then we'll come back and relate it to this. Am I going too quickly? Any questions about currents? Maybe you haven't seen this before. Yeah. Sorry. Questions? Yeah.
So basically we can make an analogy between this kind of current and like the probability current.
Yes.
That we have in kind of.
Exactly. This is very much like a probability current. Yeah.
But in this case we of course have this lattice and we have the open parameter and we have of course the lattice parameter, and it's more like more I don't know more yeah, but since we have the like the current probability, it's more like for particles, and this is a bit more like a physical approach to the system. And my question, my second question is how to apply that in the optical lattice, since this open parameter in the condensing matter is basically related with the open parameter is basically associated with the how much energy the electron needs to basically goes through an atom to another, right?
No. If you have two adjacent sites, they have the same energy. You don't need any energy to go from one to the other.
Oh, okay.
Okay? It's not a potential energy difference. It's more like a kinetic energy. So T tells you about kinetic energy, and hopping is like a motion with a velocity, which is the current. Yeah, great question. Yes? I can't hear you. Say it again. Say it again.
This the average of this operator follows or obeys some kind of continuity equation?
Yes. Yes, yes, a great question. Yes. So let me show you the continuity equation. This is in my notes, but since you're curious, I'll tell you now. So you can write a local current operator, and it's only the local current which would obey a continuity equation, because a global current isn't, well, yeah, so it doesn't have a spatial component. It's just a total current across the whole thing. But you need a local current for a continuity equation, and so the first step is to look at this thing and to say, oh, this was the bulk current. This is across everything. It's an extensive current. I'm summing over all the sites. So instead of doing that, I could just take at one site this prefactor here and combine those together and call this the operator for the local current at site J. Okay. And if I do that, then you can show that there's a continuity equation. Let's see if I can spell continuity. There we go. So continuity equation. And it's that the time derivative of the local occupation plus the current at site L minus the current at, I think it's site L minus 1, and there's a mistake in my notes. And that is equal to 0. And what does this look like? This kind of looks like the divergence of a vector current, right? And this looks like the time dependence of a local density at some place, and the sum of those two is equal to 0. And that's what I mean by continuity equations. If you want to have a local density that changes, then there needs to be an imbalance in current. So if I have a whole bunch of current moving to the left uniform, then that means that the local density at some position is constant. But if I have a current which is imbalanced, then the local density can go up, right? So the reason the continuity equation is important, let's say, in the data I just showed you, is that it's easier for us as atomic physicists to observe local densities as a function of time and then infer what the current must have been. Because actually imaging the current is not an observable that's very easy for us. Okay. If they were charged particles, you might be able to measure the field by some electromagnetic relation. But a moving neutral particle doesn't really give you a hint to hold on to as an observable. By the way, what do I mean by this time dependence here? Yeah, you can prove this by doing the time dependence of the local position operator, which is just in the same way as I defined the current operator, the Hamiltonian commuted with the local position operator. Okay, so if I put in, let's say, the tight binding Hubbard, a tight binding hopping Hamiltonian here, then you can show that this must be true. Okay. All right, so let me now talk about something called group velocity. A group velocity is a property of a wave packet. And so what I mean by that is let's consider the motion of a wave packet constructed as the sum over a whole bunch of Qs, which are block states. Okay, so these are block states, but by this, I want to have some kind of narrow distribution in Q. And in Q space, what I'm going to say is that this function is weighted, is centered at some central quasi-momentum with a width which is much smaller than the Brillouin zone size. So if that's the case, then sigma x, which will be the width in space, which is h bar over sigma q, should be on the order of what? Let's see, it has to be much greater than h bar over kl. And as you know, kl is pi over al. Sorry. So this is much greater than, let's see. To get the units right, this is 1. And this is 1 because these are all also already wave numbers. So this is then much bigger than al over pi. Okay. So I'm saying that if in momentum space, in quasi-momentum space, I have a wave packet which is small, localized in the Brillouin zone, that means it's delocalized in space. Okay, so I'm going to construct this wave packet, and then I want to ask, how does the wave packet move in position space? Well, the fact that this is a narrow distribution in Q means that when I think about quasi-momentum, and I have this dispersion relation, then I can think about the Q packet existing at, let's say, just one primary quasi-momentum. And then around that one location, do a Taylor expansion of the energy. So if we Taylor expand, then we'd say that the energy is roughly the energy at Q naught plus the distance from Q naught times the first derivative. And we can also go to a higher derivative. Okay. Okay, so if I do this now, and I want to know how this wave packet time evolves, I'm going to apply a time evolution operator. The time evolution operator is e to the I Hamiltonian time over h bar. It's this time-independent Hamiltonian. And we know it's going to happen because I've written this out in eigenstates. Yes? Because if I only keep this term around, I can tell you what it does versus time. So the answer will come in a moment. I'm going to use this, this Taylor expansion to show you that this term here determines the speed of the motion of the wave packet. Okay? Yeah, so let's see what that time evolution is. So I'm going to apply this to my wave packet, which is a sum of quasi-momenta, and then what is that? That's e to the minus I e q t over h bar times q, and now I'm going to use this Taylor expansion. Okay, I'm going to write this out as an overall phase times the sum over all these q, fq, and then the remainder in here is going to be e to the I times something I'm going to define as group velocity times q t. Okay, where does that come from? This Taylor expansion has this derivative. And so now I'm just going to define this, and you'll see why in a moment, as h bar times the group velocity. Okay. And then there's higher order. So if I ignore this higher order and group these terms, there's q-independent things, and then there's h bar q v group. Okay, so the q-independent things are what I clustered out here as omega naught. But this ends up in here. And I forgot to write q. Okay. So what does this operator do? Remember that this looks a lot like the translation operator. Okay. If I have something which is e to the I v group qt, this is let's see. see, maybe I wrote this down. Back here. Okay. So I've told you that there's this, translation operator, and you can see that coming up here again, where I have e to the I q xj, and so this is just a translation of each of these states, okay? Sorry. So this is a translation. There's a time dependence in this position, okay? This looks like e to the I v group times time times q of the q states, which you could just write out as some kind of linear translation in position versus time. Okay, so I'm showing you that in this approximation, that if I time evolve the wave packet, I get some kind of overall phase that doesn't matter much, and then I get a translation at v group times time times the original wave packet. And so that says, to the extent that that dispersion relation is linear, I have a wave packet which just translates. Okay. So this seems like unrelated to optical lattices, mostly. But now let me try to put those two things together, which is, why is the group velocity telling us about how things move when I just told you all those current operators are the way things move? And the proof of that is as following. If I take the derivative of the dispersion relation, then I want to take the derivative of the expectation value of my Hamiltonian with Q. And because the Hamiltonian doesn't explicitly depend on Q, then I need to write out, kind of by the product rule, something like this. So the time derivative, the Q derivative is something I can find really easily if I write out the block function in terms of the Wannier function. So I told you this was kind of like my favorite trick for this lecture, and here's an example. I'm going to write out Q as the sum over all the Wannier states at some location xj. So I'm now just differentiating this exponential, and I pull out an I xj times all these things. Okay. But now I also know what this is. Remember, I told you that this is the same thing as WQ bra ket with a Q, like that, right? And so this is then I times the sum like this times Q, and this is what I defined earlier as the center of mass operator. So if I take the time derivative of the Q derivative of the block function, I get one of those center of mass operators. And And what's going to happen is if I now put that in here, and I put its complex conjugate here, then here I get basically a center of mass operator. Here I get a center of mass operator with a minus sign. And notice I then have the commutator between XCM and H, right? Because H is here. And so modulo constants, you can see that this ends up being that the derivative I took to get that group velocity from the dispersion relation is now just the expectation value of H XCM times constants, but this is, of course, the expectation value of the current operator, which I defined. And so it makes sense that I call this the group velocity. Like current, group velocity is showing you how things are moving around. Okay? Okay. So I have 10 more minutes. I want to tell you what happens when I apply an external force. As I said to you, yeah?
What are the orders of magnitude to the group velocity?
Yeah, great question. I can show you a kind of so if I took the tight binding relation, okay, so this is tight binding here, then you know that this whole bandwidth is 4 times tunneling. And then you know that this distance in quasi-momentum is, in the units I've been using in this lecture, this is pi over AL. So basically, the question is, what's the slope of this energy versus Q curve? And it's just going to be T times AL, right? So I take this derivative, and now I have this velocity. This is the group velocity. And the maximum here is going to be AL times tunneling divided by H bar. So the order of magnitude is given by the tunneling strength and the lattice coefficient. Good question. OK. So let's apply a force and see if we get a current. So when I apply a force, I break some of the paradigms I've been talking about so far because I have a Hamiltonian, which is the original, lattice Hamiltonian. But now I'm going to add another thing, which is an X operator with a force in front of it. And the problem here is that this is not translationally invariant. So we have a problem because everything we've done from like the very first equation I wrote on Friday said we have discrete translational invariance in this problem. Okay. So the way we fix this is we go into a different frame. And in that new frame, we're going to get rid of the gradient. You can think of that like an accelerating frame. Okay. And when we do that, we'll restore translational invariance. But then we won't be in the original frame. So we won't be solving our original problem. But what's nice is if we get rid of this gradient, we can apply Bloch's theorem again, find these translationally invariant solutions, et cetera, et cetera. And then to find a solution to this problem, we just transform back. Okay. So the approach is go to a problem you can solve it, and then unmap backwards, and then you find the solutions here. I do that in my notes. There's no way we're going to do that in 4 minutes. But let me tell you what you find. You find that the time derivative of the quasi-momentum is 1 over h bar times the force. And that's really great because this is kind of like F is equal to dp dt, right? This looks very Newtonian, except it's not momentum, but quasi-momentum, which reacts to the external force. On the other hand, if I want to know what the group velocity does, I have to ask a different question. The time dependence of the group velocity is not just a linear relationship to the quasi-momentum, because remember, group velocity is the derivative of energy with respect to q. It's not even linear with quasi-momentum. So instead, the way we figure this out is we say, let's take the time derivative of q, which we know, but then use the chain rule to take the q derivative of the group velocity. But this, I just told you, is equal to 1 over h bar times the derivative of the energy with respect to q in the first place. And so combining these things, I now have dq dt, which is f over h bar, and then I have another h bar from this derivative, and I have the second derivative of energy with respect to quasi-momentum. And so now I have kind of F equals ma, if I put things together correctly. Let's call this the acceleration. Acceleration should be force over mass. So this is force over the effective mass, which I'm going to call m star, so long as the effective mass is defined as 1 over h squared times the second derivative of the energy with respect to quasi-momentum. So this is called effective mass. Now, effective mass is a strange thing. Let me show you why it's strange. So if I take, for instance, this tight binding relation, then if I place myself here, everything looks great. I have a velocity which is linear in momentum, which is just like free space, and I have a mass which is a positive value. But now if I go further along, and let's say I move to here at q is equal to halfway into the Brillouin zone, now, okay, velocity has saturated to the maximum possible group velocity, and 1 over the effective mass, which is what the second derivative is, has gone to 0. That means the effective mass has diverged. It gets worse because next, you might consider what happens if you go out to the edge here. And so then group velocity is a decreasing function with q, which is already strange, okay? At least it has the same sign. But here, effective mass, in fact, all along here is negative. So it means that the acceleration is backwards when I push forwards. Why is that? Can you think of a physical reason that a particle would go this way when you push that way? Like a restoring force.
Yeah, exactly.
What is the restoring force? Where does it come from? No, but I'm not asking about the particle pushing on my finger. I'm asking about why the particle goes this way when I push on it that way. So third law is always asking about a different actor in the problem. What else could push you backwards? I have an external force going this way. What else is there around that could do anything? Like if you run into another particle? Yeah. Yes, could be, but we haven't put other particles in our Hamiltonian yet. So this all happens for a single particle without interactions yet. Well, what else is there in the problem?
So
Physically,
you could think about Coriolis force, like if you became a non-inertial method, a non-inertial frame, and then you could feel the opposite force.
could be. What's in the Hamiltonian? Yeah. Yeah, that's right. There isn't just this force, there's this thing. You know, this can apply a force on a particle. It's a lattice. So why would a lattice, when I move to the edge of the Brillouin zone, why would a lattice push you one way or the other? Maybe. What kind of atom-light interaction or scattering did we talk about on Friday? Bragg scattering. Yeah. Bragg scattering is the thing which is strongest when I get to the edge of the Brillouin zone. And so when I'm in the middle of the Brillouin zone, it's not very strong yet. Maybe it's infinitesimally weak. But as I move to the edge of the Brillouin zone, the reason that plus KL couples to minus KL is because there's Bragg scattering. Okay, once I get a kick backwards, the momentum of the particle, the atom, will change from positive to negative. But that has to happen adiabatically as I move quasi-momentum towards the edge of the band. It has to happen adiabatically because the quantum state is going to smoothly evolve from one to the other of these states. So as I'm getting there, the light forces on the bare particles is going to be stronger. Okay, so my time is up. Let me just say one more thing about this other point here, where I said the mass diverged. That might have bothered some of you. Divergent mass seems terrible. Dispersion relation, right around there. So what that means is that the group velocity is maximum. So for a small perturbation in quasi-momentum, which is what I get when I push on this thing, how much does the velocity change? To first order, the group velocity doesn't change at all when I'm at the maximum. So if I want to describe a particle where I apply a force and the velocity doesn't change, it's quite natural to say it's like it has infinite inertia. I'm not able to accelerate it. Okay, so the divergence of the center of the effective mass here just means that the group velocity is to first order independent of Q. All right, I'll stop there. Thank you.
More questions?
Professor, I would like to ask you about tide binding. Could you say about relation between tide binding and tunneling?
Yes. Are you asking for the physical approximation or how I define binding, or what is
Physical relation.
So I think this is some description of tight binding here that I'm saying the process of nearest neighbor tunneling is the dominant process. So I guess if you look at this plot here as a function of lattice depth, then the closest tunneling, which is this T of 1 here, is the strongest process. And the relative strength of nearest neighbor to next nearest neighbor gets larger and larger as I get the lattice deeper and deeper. And so the tight binding approximation is essentially to say I neglect these other processes. Does that answer your question? Okay.
It's just that the part about the problem with the translation symmetry. If you could just repeat your argument to how you solve the thing and that problem. Just the argument, that the physical argument, to say that you move from a different frame and just that part.
Yes, yes. Okay. So let's see. Yeah, the transformation I apply is a gauge transformation. So in a sense, it's a kind of gauge transformation you use in electricity and magnetism, where if I consider it to be an electric field, the electric field is the time derivative of the A, the vector potential. And you know that I can write a unitary transformation, which is e to the I A, okay, e to the I A time, and e to the I A times x operator. So that's the unitary transformation that takes me from this problem, which has essentially an electric field in it, which is what this force is, to a problem with no electric field. I gauge it away by writing an additional phase on the wave function. And so when I write that additional phase in the wave function, I now have a new wave function which has no electric field in its frame. And when I do that, I still have the periodic part and all that. So I've transformed this problem to one where I restore translational symmetry, discrete translational symmetry, and now I go through all the math we've just done. I find there are block functions, and I know what they look like, and I can solve for them, et cetera. And then if I want to know what happens in this, I translate back, and it turns out I get this Q, this quasi-momentum, which is ramping linearly as a function of time, which is kind of like what a charge does in an electric field. It ramps linearly as a function of time. It accelerates the Coulomb force. Yeah, so that's the transformation. It's in my notes, so you can see it on the Dropbox now. Yeah.
More questions?
All right, thanks for your attention.
Coffee break. Thank you very much, Joseph. So we meet again at 4 o'clock here.